Hi, everyone. Okay, so welcome to 16A discussion. I just wanted to let people know there's like some midterms over here, so we're going to pass them around. You're like welcome to grab one for practice later, but we won't actually be using them during the session. We just had a lot of midterms that we don't need. So, okay, that's all. These are midterms from last year, by the way, so not this year's midterm.
Hello?
I think if you talk closer to it. Hello? But like, we just have to speak into it. Like, keep it close. Like, hello? Hello. Is that working? Hello, everyone. Okay. Hello. Could I have everyone's attention, please? Thank you. Welcome to EEC 16A, the Midterm 2 review. My name's Anika, and with me I have some other really wonderful TAs. We have Alice, Moses, and Miyuki. And so today we're going to be going over, a little bit of content from throughout what will be on Midterm 2. And so hopefully this will be very helpful. So talking a little bit about what's going to happen. We have a lot of slides where we're trying to cover all the topics that we have discussed since Midterm 1. And we're going to go quite fast. But these slides are available to you, and there's actually a Piazza post out right now with it. So if you want to open it and follow along there, you're more than welcome to. If you have any questions during the presentation, you can just raise your hand. One of us will come by and answer your question. We may answer some of the questions up front. So we're just trying to get to your questions as soon as they come by, so make sure to ask lots of them. And then just a little thing about scope. Op-amps are not in scope for Midterm 2. And so, yeah. And the last thing is that there are exams coming around. There's that box right there. This is a past midterm, so if you just want a copy of that to practice, feel free to grab one. And so with that, this is our agenda. We're going to talk about all these various different topics, and then we'll also go through some practice exam problems. Okay. Some people really want to be here. Okay, so with that, we'll just get started. So, starting off, a couple important circuit elements, resistors and capacitors. So remember, when we're constructing this, for resistors, the resistance of something is rho L over A. Rho is the resistivity of a material. L is the length of the object that you're trying to find the resistance of. And A is the cross-sectional area. For a capacitor, this is epsilon A over D, where epsilon is the permeativity of the space in between the two parallel plates. A is the surface area of one of the plates, and D is the distance between the two plates. Okay? The IV relationship for resistors is the all-important Ohm's law, V equals IR. For capacitors, this is Q equals CV. We're relating charge to capacitance and voltage. If we take the derivative of this, we get current is equal to the capacitance times the change of voltage over time. And then we also have this series and parallel equivalence. So for resistors, if you have two resistors in series, you can just sum up the individual resistances. If they're in parallel, then we have 1 over the equivalent resistance is 1 over the resistance of each of the individual resistors in the parallel. Okay? And then for capacitors, this is kind of flipped. So if it's in parallel, then you're summing the capacitances together. Okay. Another just key important point, we have V equals IC over T. This is from the previous form that we had if we just integrate it in reverse. But this is only true if current is constant. Because otherwise, when you're taking the integral of current, if it's a function of time, then it's going to be a little different. Okay, a voltage divider. This is a very interesting circuit configuration that comes up a lot, so it's really good to know. What this is pretty much we have two resistors dividing a voltage, therefore the name. And so we have the voltage across the second resistor, just the second one written right here. It's just the voltage source, and then R2 over R1 plus R2. Okay, and the same thing if we want the voltage across the first one. Yeah, I believe so. It's in kind of parallel to this. If you look at the discussion worksheet from today, you'll actually see that. Yeah. Okay. So we talked about a voltage divider. There's also a current divider. As you would guess, it's dividing the current. And so here we have a current source, and then we have two resistors. Now, instead of in series, they're in parallel with the current source. And so here we have the current through any one of the resistors is the current source times the opposite resistor over the sum of the two resistors. Okay? So note that it's opposite. And then finally, power. P equals IV is a formula for any circuit element. Okay? But if we decide to say that we're trying to find for a resistor, well, we can use V equals IR, and so we can get, if we plug that in for V, or if we plug in V over R for I, we can get that the power is I squared R, or V squared over R for a resistor. And power is always conserved. Okay, so the sum of all power in a circuit will be 0. If the sign of the power is negative, that means power is delivered to that item, or that element is dissipating power, is delivering power. And then if the sign of the power is positive, that means power is dissipated by the element. Okay. And remember for this to follow passive sign convention, right? So current goes from positive to negative terminal. Now I'm going to pass it on to Alice.
Oh, thank you, Anika. Okay, so the next section we'll talk about is about different techniques we can use for solving circuits. So we've covered a lot of different techniques already. KVL, which is Kirchhoff's voltage law, KCL, Kirchhoff's current law, and also Ohm's law. So these are sort of like the basic ones that everything else is built upon. We've also learned about different types of equivalent circuits that we can take to help simplify our circuits. So if you notice that there's like resistors or capacitors in series or parallel, you can also use those to help simplify your analysis. We've talked about node voltage analysis. So this is sort of like the most general thing to do. So if you're super stuck and not sure what to do, node voltage analysis is always possible to solve. So that's one method to try. And then lastly, we'll also talk about superposition and then Thevenin and Norton circuits, equivalence. Okay, so the first thing, super important thing, is to know how to identify what is a node inside your circuit. So a node in a circuit is a section of wire that's at the same potential. And so only if you cross some component like a voltage supply or a resistor or something is the potential going to change. So we have like a great method for how to figure out where your nodes are. And so this idea is we can just start somewhere and just color in all of the area until you hit a component. So this will make a bit more sense in this example. So let's say that we have our simple circuit. It has like a DC voltage source and a few resistors, right? So let's say we start off on sort of the top corner. So I can start and go ahead and color in that section and like everywhere until I hit the first resistor, and then everywhere until I hit this end of the voltage source is going to all be part of the same node. Okay? And I can go ahead and do this with every other section of wire inside my circuit. So here I've colored in all of the wire over here. And then I can also color in all of the wire over here. Okay, so in total, I have 3 different colors. So therefore, 3 different nodes in my circuit. Hooray. Okay. The next thing to know is how to identify whether something is in series or in parallel. And so this is something that can really easily be mistaken a lot of the time. But the key thing to note here is that you have to make sure they have the same exact current through both of the elements. Then you know that those 2 elements are going to be in series. So this means that they don't have the same value of current. They have to have the same input current equals the output current, right? So here I have 2 examples. So this current and this current, if we do KCL at this node, we know that the current going in equals the current coming out. And so therefore they have the same current and they're in series. This example, we've set both of the currents to 1 amp, but they're not in series because some of the current also comes out through here. And so even though they have the same value of the current is not exactly the same, therefore they are not in series. This guy here, you'll notice that even though you have kind of two resistors connected at the same node, some of the current is also coming out through this third wire. So again, it's not in series. Another way you can think of it, instead of thinking about the same exact current, is you can also consider if you have like two elements that are connected at the node and like nothing else is connected to that node. So those are sort of like equivalent things to say. Okay, so next let's talk about when things are in parallel. So we know that things are in parallel if they're connected to two of the same nodes on both sides. Not just one side, but both of the sides. So this example over here shows two resistors, and we know that they're in parallel because they're all connected to one node here, and they're also connected to the same node at the top. What about these guys? These are also in parallel, right? Even though this capacitor in the middle looks kind of funny, if we think about where the nodes are, this whole bottom wire here is all the same node, and the whole top wire is all the same node. So these three capacitors are all in parallel. So looking at this last example, these are not going to be in parallel because if we take a look at the top node, basically the two resistors are sharing one node in common, but on the other side, they don't share a node in common. And so because not both of them have the same node, those are not in parallel. Any questions about this so far? Okay. Okay, another thing we want to talk about when we're analyzing circuits is how to know what ground is. And so you can always think of ground as some reference point where you're saying, like, this is where we're going to set 0 volts to. And an analogy you can take with that is you can think of it as the same thing as like elevation, right? So if I'm, having a great day at the beach, I'm probably going to be at about 0 feet relative to sea level because I'm right next to the ocean. But if I take the reference next to, let's say, Mount Everest or something, I'm going to probably be at like minus 5,000 or 10,000 feet, right? So, depending on where I set my reference point of like what 0 is, that will tell me my relative height relative to what that reference is. And so ground is the same thing. That's saying where my reference point is for 0 volts. And then every other voltage, every other node voltage in your circuit will be written in reference to where you set your ground. But it doesn't matter where you set it. You can set it anywhere because the relative difference is always going to stay the same. Okay, so once all of those things are very clear, the next thing we can talk about is sort of one method to solve circuits, which is node voltage analysis. And so we have these steps here. There's also a note on this on the website. And so we kind of have like a bunch of different steps. So I'll kind of just talk through them very quickly. So here I have an example circuit. So the first step is always to set a reference node or a ground somewhere on the circuit. So you can basically pick any spot. So I picked this spot on the bottom. The next step is that we want to label all of our nodes with known voltages. So in this case, because we have a voltage source, we know that the voltage at sort of the top area is known voltage, and that's the only one we know. So we can go ahead and label the voltage at that node. Next step is to label the remaining nodes. So there's one other node remaining besides the top node and the ground. So we can label that one too. And the next part is to label all of our element voltages and currents following passive sign convention. So we can go ahead and label that. So if you'll remember, passive sign convention means that if I have a positive and negative sign for my voltage, the current is going in through the positive end and out through the negative end. Okay, so then after this, we can write out our Kirchhoff's current law equations at each of the unknown node voltages. So in this case, we only have one unknown node. So you'll notice that the input current I2 equals the output current of I3. Then we can write out all of our element current equations. So in this case, we can take the input current I2 as the difference in the voltage nodes across that current divided by the resistance. And then repeat this as well for the R2. And then after that, we substitute it back into our initial KCL equation and solve it. And this will give us our voltage. So once you find the node voltages, you can kind of go back and calculate any currents you need to. And in this way, you can solve for every current and voltage going through your circuit. Another common question that people have is, so what happens if we flip the labeling of our current direction? So here in this example, I have the same circuit, but one person has labeled their R1 current going this way, and the other person's labeled the current going that way. So in this case, if we were to go ahead and take our KCL equations and then also our element equations, you'll end up with something like this, right? So you'll notice that you don't get the same KCL equation, and then also your element equations are different. So this one is going to be the negative of this one. However, when we substitute all of our equations in, things will still work out in the end if both people did it correctly. By rearranging our questions, we'll see that actually you end up with calculating the same voltage at that node. And you'll notice also that the current for one person will be negative to that of the other person. But that's okay because that means that the real direction of the current is both going in the same direction. Another thing that it's highly suggested to do before you start solving with something like node voltage analysis is to try to find as many ways to simplify your circuits as possible. So in this example, if we kind of take a look at the blue box over here, if we have two voltage supplies in series, we can actually combine those, right? So I can make V1 and V2 into V1 plus V2. And then if I take two current sources in parallel, I can also combine those and add them together. So I'll get I1 minus I2. And then the red one just shows two resistors in series and then two, resistors in parallel. So by doing this, you can sort of reduce all the nodes you need in order to actually solve it. And this makes things a lot easier. One other thing that we can also consider doing is converting between Norton and Thevenin equivalents in order to reduce our circuit further. So that in this example, basically we can take our voltage source and this resistor in series and convert them into parallel. And so now we have one current source, but three resistors in parallel, so that makes it easier to solve compared to this one where we have only two resistors in parallel. Yeah, question. Yes. Yeah, and so actually, if you have something like two voltage sources in parallel, it's hard to say because the voltage across the node has to be the same, and so it's a it's a non-realistic type of circuit. Mm-hmm. Okay. Okay, so one thing to mention about if you decide to do any sort of simplifying method is sometimes you can, after doing all the simplifications, you'll find some quantity, but it doesn't tell you exactly what you're trying to solve for. So it's just good to keep in mind that after you've kind of simplified away your original quantity, you might have to go back to the original circuit to solve for the original value you're trying to solve for. But even still, by simplifying it, you'll know some new thing that helps you solve the original quantity better. Okay, so I have one more thing to talk about, which is superposition. So superposition is basically a method to help us solve for something, and it's good to use it if you have multiple sources and you don't want to consider all of them at the same time. So basically what superposition is saying is that we can have linear elements such as current or voltage, and the current or the voltage going across or through an element is going to be based on the sum of like the current or the voltage affected by like each of the individual sources acting one by one. So what we can basically do is, so basically like zero out one source, calculate due to the other source, zero out the other source, and calculate due to the first source. So why does it work? So one thing that you can consider is that if we were to go ahead and take sort of like the node voltage equations for this circuit, so basically like I think the blue line is representative of the first equation, and then the pink line is representative of the second equation. We can go ahead and like convert this into a matrix. So hopefully some of you remember this from like before midterm 1. And so you'll notice that in this matrix, we have like some terms in like the V matrix part that's like dependent on V and also I, which are like the current and the voltage sources, right? And so we can actually break this down further. So if we go ahead and do our superposition circuits, you'll sort of end up with like some equations with some terms that you're solving for, which is x, which is equal to something due to sort of the voltage source, and then same thing with like when you apply the current source, right? And so because we know that like the currents and the voltages are linear, we can sort of add these terms together, right? So your final expression should be in terms of like basically like U11 plus U12, and then also U21 plus U22. Oh, okay. Okay, so that's all. So now I'll let Moses take the floor.
Thanks, Alice. Okay. So all right, so for the next topic, we'll be covering Thevenin and Norton equivalents. So in particular, these are important because they simplify analysis for a lot of circuits. If you can represent a circuit in terms of just two components, a source and a resistor, then you can calculate things like how much power is dissipated in my load, or how much voltage or current do I have going through the load. So in particular, one thing to note about this is that when we say equivalent, it follows that same definition of equivalence that you're given for like resistors and capacitors, which is that if you think about the voltage and the current that you see on the terminals A and B, these will be identical to the voltage and the current that you'd see in the original circuit if you were to rewrite that original circuit as either of these. So one thing to note is that not all circuits have an Thevenin or Norton equivalent, and you might have seen this in one of the discussions with just a single voltage source or a current source. But if it's sufficiently complicated enough, then so that usually means like a lot of resistors, a lot of sources, then you can usually find one. So one thing to note about the process for finding Thevenin and Norton equivalents is that there's three quantities that you're interested in, which is you want to find the V Thevenin, find the I Norton, or the resistance in the corresponding circuit. If you find two of these three quantities, then you're guaranteed the third. So really from these methods up here, if you follow two of them, then you can find the third for free. And you already get the Norton and the Thevenin equivalents. So in particular for V Thevenin, you'll note that here there's NVA and superposition. So when you're looking for the Thevenin equivalent, you're going to want to look for the open circuit voltage on the terminals A and B. This can be done by either of these two methods, depending on how many sources you have. Likewise, for the Norton current, it's going to end up being the short circuit current. So if you take your circuit, connect a short from your terminals A to B, and then look at that current, then that'll be exactly your Norton current. For your R Thevenin or R Norton, you're going to, if you already happen to find B Thevenin and I Norton, you're going to take those two quantities and then divide one by the other. That'll give you the resistances. Some other methods that are covered in the notes is if you turn off all the independent sources in a circuit and you're left with only resistors, then that equivalent resistance that you see in the terminals A and B will end up being your Thevenin equivalent resistance or your Norton equivalent resistance. The thing is, this method is only applicable if you happen to have, no dependent sources. If you have dependent sources, then you have to use an alternative method, which involves turning off of the independent sources, and then you have to supply a test source on the terminals, and then look at the ratio of the test voltage and the test current. So if we look at why it is that we are looking at like the open circuit voltage and the short circuit current, let's say we have this black box that represents some circuit that we're trying to analyze. And let's say it does happen to have a Thevenin equivalent. If we substitute that Thevenin equivalent on the inside and then look at what happens when we keep the terminals open, you'll see that no current will flow through that resistor, and you'll just have V Thevenin appear on the output. Likewise, if we short circuit the output, then all the current will have to go through that resistor, and if we short it, then essentially there's nothing else like taking up the voltage. So you'll see the entirety of the voltage over that resistance. And so if you measure the short circuit current and you already know the open circuit voltage, then by Ohm's law, we can find out what the Thevenin resistance will be, because there's no other like resistive path here. This is just a short. So likewise, for the Norton equivalent, we can do a similar analysis for looking at why it works out when we look at the short circuit and the open circuit quantities. And in particular, you'll see that all the current in the short circuit situation will have to be diverted through that short. And then if you keep it open, then all the current will be diverted through the Norton resistance, and then from there you can find out what that resistance has to be, because you found out what the Norton current was before. So if you want to find the Norton or Thevenin resistance, then as long as you take the ratio of those two quantities, or you have either of like the Thevenin or Norton circuits, you can always find that resistance. So some things to remember when you're doing this analysis. Was that when you're turning off independent sources, this is much the same as you would do in superposition, where if you have a voltage source, you're going to turn it into a short or a wire connecting those two nodes that you have. For current sources, you're just going to replace with the open circuit. So essentially, you're just going to create a break in the circuit. For dependent sources, you can't turn them off, and they only turn off if they depend specifically on a independent source. So for example, if you had a dependent source directly dependent on something else that went to zero, then you can turn it off. But for purposes of like finding the equivalence, you have to keep these around. There's a question, 2 questions. Yeah, we'll look at that on the next slide. Yeah, and then there's another question. Okay. So a last point about Norton and Thevenin equivalence is that they're going to preserve the behavior of the circuit outside the box. So when we look outside the box, there's some current and voltage with which these circuits behave. But if we're talking about in terms of like looking at, what's the power dissipated inside our circuit, the Thevenin equivalent or the Norton equivalent will not model that accurately. So if you want to do like a power analysis for what power is being dissipated inside your circuit, then you actually have to look at the actual circuit. You can't look at the equivalent, because the only quantities that carry over are the voltage and the current. So here, there's a slide about dependent sources, and I'll cover this real quick. In particular, they're not on the exam. Professor Boser noted this in one of the Piazza posts, I think, on the midterm like scope page. So if you want to know, then you can look at that follow-up. But essentially what dependent sources are any source that depends on some other quantity in the circuit, so either voltage or current. You can have a voltage that's dependent on another voltage or current, and you can have a current that's dependent on a voltage or current somewhere else in the circuit. So in particular, like notationally, you might see diamonds or circles. Either of these are valid. The way that you know it's a dependent source is if the value is dependent on some quantity that's not necessarily like known right away. So from here, I'll hand it off to Miyuki.
Okay, so we'll be talking about comparators. They have the same shape of an op-amp, which you will see on some of the previous midterms, but we are not testing on op-amps, so don't panic if you see something like that and you don't know how to do it. We're just testing on comparators for this midterm. So a comparator is just this triangle is represented by this triangle shape, which has a V plus and a V minus, which we'll be plugging into the comparator. And it's powered with a VDD, which is our like higher voltage, like 5 volts, and VSS, which is our lower voltage, like ground or 0 volts. And it'll output a V out or a V comparator, which is going to be either VDD or VSS. It'll be VDD if V plus is greater than V minus, and VSS otherwise. So you'll just get one of 2 options with a comparator. So if we have a circuit like this, where we've got our voltage divider, and we have some other reference voltage that's 2 volts, we want to look at for what values of V in will, what will V out be. So if the voltage at U1 is greater than the 2 volts that's going into V minus, then we will get the VSS as our output voltage, or 5 volts. And then vice versa, it'll be 0 volts as our output voltage. And then we have to note that no current, I plus and I minus, is going into the comparator. Because if there was a current, then that would change our voltage U1. But since there's none, then we know it's just the voltage divider equation. Sorry, I meant VDD is 5 volts. Yeah. And we can see with this graph that V out will be low at 0 volts until V in reaches 4 volts, in which U1 will equal the 2 volts, and it'll jump to high. So we're going to be doing some past midterm problems now, and I'll be going first with the summer 2017 midterm 2, question 9. It's not the one that was handed out, but you can find it on the website if you scroll down if you want to use it on your phone or tablet. But we'll also have it up here. Well, I was just going to... Oh, we should have mentioned this.
Like, you want to post something, so just let me post it.
I know. It's... So... I'm going to write on this.
Yeah, no, we'll zoom on them just so they can read the problem.
They got very chatty. All right, take a second and look at it, and then we're going to go through how to solve the problem. Can you hear me okay?
It's a bit quiet. I don't know. I find like I have to hold it really close for it to pick up.
I know. I just like also have to write.
Yeah, that's true.
All right. Okay, so let's start with part A, which is our very common circuit. We've got a current source, and it's charging a capacitor. So we're talking about the capacitive touchscreen problem here, but this is just a more simplified version. We're not looking into the mechanics of it. So we're trying to find the slope of this line. And we'll start by just writing what we know about capacitors in relation to current. So our most commonly known equation for capacitance is the charge, Q, on the capacitor is equal to the capacitance times voltage. We know that the capacitance is C screen, and the voltage is V1 of t. If we take the derivative, dq dt, we know that's our current, which is just the flow of our charges, is equal to c screen, which is a constant, times dv1 dt. Then we'll have to take the integral of both sides. So I'll do some calculus here by rearranging. We've got dv1 equals is over c screen. And then we'll rearrange it so we can take the integral of both sides. So I move the dt over up here. And so we'll integrate from t equals 0 to t equals like capital T. So this is dv1 of t. So we'll get that the voltage 1 at t minus the voltage at 0 is going to be equal to is over c screen times t. And note that is has to be a constant source, because if this was a function of t, then it would change our integral. And so it's t minus like 0, but we know like that'll just disappear. Also, we know that this will go to 0 because it's initially uncharged. But sometimes it'll start with a charge. So that's something to not just forget about or just write the equation without that. So if we look, our equation is v1 of t is equal to is c screen times t. I guess this one's capital. But that would make our slope just is over c screen. Starting from here? Yes, you could. I mean, to get to this equation, you need to integrate. Oh, that's true, yeah. You can start from this. You don't have to do the integration. This is just a good way to remember, especially if you have a more complicated circuit with different capacitances and, like, different equivalences and whatnot. All right. So let's look at part B. All right. So now we're looking at if we have another capacitor in here, which is our C finger if we're touching it. So there are two capacitors in parallel. And we're trying to figure out what is the correct plot, where V1 is the voltage in the part A, and V2 will be voltage that we will calculate in part B. So we know that our equation for the last part, so V1 of t was just is over c screen times t. That was for our general setup. One current source and one capacitor. But now we have two capacitors, so we can just notice that we have the same node on the top and the bottom. So that means they're in parallel. So we can equate them by using the parallel configuration. So you've got is, and then when they're in parallel, we'll add them because they're capacitors. So that was our V1. So this one's our V2 of t. And we can use our same equation as last time, but now we'll use our C equivalent on the bottom. So so this is C equivalent. V2 of t is equal to IS over CQ times t, which is just IS over C screen plus C finger times t. So when looking at our two plots, which voltage is going to be greater? Or what slope is going to be greater? The slope of V1, which is IS over C screen, or the slope of V2, which is IS over C screen plus C finger? In this case, we can see that the slope of V1 is greater than the slope of V2 because there's a larger denominator on V2. So this one is our correct answer. We are assuming that they are initially uncharged in this case. So there will not be any charge on it before this light. So, or we're assuming like V2 of 0 is going to be 0. Okay. So now we're going to look at part C. And so for part C, we're taking our configuration and we're plugging it into a comparator. So they usually have this symbol. And we'll have a reference voltage. And we're trying to choose a reference voltage such that that when you touch it, the output, Vout, will be a different voltage than when it's not touched. So Vout touch does not equal Vout no touch. So we want to choose, using this graph, a reference voltage that will give us different values. So we'll remember that V2 is on bottom and V1 is on top because it's got the greater slope. And we're assuming that these are going to start from uncharged in both cases. So for instance, I'm just going to use my comparator to check, like, if I wait, like, for some specific amount of time, T naught, so maybe like a second. I wait a second, and it'll tell me if it's touching or not. And then maybe I do touch it, it'll wait a second, and then it tells me it is touching. And that's assuming these are starting from uncharged. So where do you think on this graph we'll put a horizontal line that will be our Vref? Yeah, between the two lines. So we wanted to go somewhere here between the two lines. So, so what will be Vout touch? Will that be VDD or VSS? Why don't you guys talk about it amongst yourselves? See what you think. Will it be VDD? Alright, so what do we think? So what will V touch be? VDD or VSS? Hey guys, guys kind of come to a consensus? What do you think is V-touch? Or, yeah, V-out touch. I think I heard it. It's going to be VSS, because V2 is representing our V-touch, or when it's the case where it's touching, and V1 is where it's not touching, and V2 is below the reference voltage in the threshold. So it'll be the lower voltage VSS, and then no touch will be VDD. All right, we're going to go on to a new problem now.
Thank you, Miyuki. So here's another problem. So take a look at it, discuss amongst yourselves, and then we'll go over it together. Okay. Is everyone good? Could I have everyone's attention, please? Awesome. Thank you. Okay, so in this problem, we're told about this device called a MEMS accelerometer. And ultimately what it is we're told that there's this T-shaped... so we got this T-shaped device right here that moves up and down based on the acceleration. And ultimately what we are trying to do in part A is say find the capacitance between the stem of the T-mass and the sidewall as a function of x. Right, so that's our first task. So, we may remember that for a physical capacitor, we have this handy way of finding it where C is equal to the epsilon, which is the permeativity of the space between it, A, which is the surface area of the plate over some D, the distance in between. So the idea is that we want to figure that out for this given device, right? So first we're trying to see where is this capacitance that they're talking about. So they say it's between the stem of the T-mass and the sidewall. So this right here is the stem of the T-mass, and this is the sidewall. Okay? And so let's start by going through this. So we read up above, and we see that all structures are made by metals separated by air. So that means for our epsilon, for the permeativity, we can just use the permeativity of free space, which we know is written as epsilon naught. Okay? And then for the area of the plate, well, we're only the part where they actually overlap, right? And so we have this X amount from here to here that it kind of attaches, and then over up here, we have some amount here, and this is kind of what I've shaded in here. That's kind of the parallel plate that the two kind of have this space in between, right? And we're told here that the width here is W, and this height here we know to be X. And so just, length times width, we figure out that this area should be W times X. And then for the distance between the parallel plates, we look right here and we see that we're given that this distance is D. And so ultimately, that's what we know the capacitance between this T-stem and one of the sidewalls is. Okay. Then it says, find the net capacitance between the two terminals N1 and N2, assuming the only parallel plate capacitance is that of the T-mass stem and the sidewall. So saying these are the only capacitances, what is the net capacitance? So what are the capacitances we have? Well, we have this one right here, but then we also have the other side. So we have this other side of this T-stem and this sidewall over here. So we have two parallel plate capacitances. Now we need to figure out how are they connected, because we want the equivalent capacitance between N1 and N2. So are these connected in parallel or in series? What do you guys think? Parallel. Okay. Yeah, I'm hearing a lot of parallel. And the reason they're in parallel, which is what, Alice was explaining to us earlier, because we have N1 and N2 as our two nodes, and they're both connected across like that. So if we have two capacitances in parallel, we know that the total capacitance is just the sum of the two individual capacitances. Here we know the two capacitances are equal, and so our net capacitance will just be 2 times C. And that's the C we found above. Okay, any questions about this part of the problem? Yes. Well, it's kind of connected through this path. Oh, sorry. This path right here. We're just told that we do not have to assume this part up here is a capacitance, so we can just think of it as a connection, as a direct connection. Right? It's through ignore that line right there. But does that make sense? So, apologies that this is black over black. But these are the two parallel plates right here, right? They're connected from N1 through here, and then they're connected to N2 via the sidewalls. Does that make sense? That's a good idea to draw it. Yes. So we're told that we don't have to worry about those. We're told right here, it says, assuming the only parallel plate capacitance is that of the T-mass stem and the sidewall. So because of that, these are the only capacitances we have to worry about. Any other questions? Yes. Why these are sideways like this? The idea is pretty much, we know that our parallel plates, right, is this portion of the sidewall that we have shaded in right here, and it's going to be the same thing on this sidewall, just kind of in the hidden side to us, right? And so those form our parallel plates, and so whenever we draw a capacitor like this, we're kind of representing it as this is one of our parallel plates, and this is the other one. And so because of the fact that these are side by side like this, that's why we kind of draw it on like that. Okay, if I draw it to the side, just kind of paralleling that, can everyone see that? It's first off, okay. So we have N1 up here, right? It comes like this, and we have our parallel plate with the left sidewall. We have the parallel plate, the right sidewall, and these both connect to N2. Right? And so the reason these are parallel, if we redraw this nicer, we can say N1, we can kind of just turn these around, and so it just, maybe this is something that we're more familiar looking at. Okay. Any other questions? Okay. So we have another part to this question. Okay, so here it is. There's parts B and C. They are related, so why don't take a couple minutes to read through this. Okay. Right. Thank you. So this is part B and C, and so here we have another circuit kind of laid out to us, and we're told that there's two sorts of phases for us. They've kind of drawn out each of the phases. This is phase 1 and phase 2, one where the voltage source is connected to CA, and the other one where it's not. Okay? We are also told that all capacitors are initially uncharged, so that might come into play. And then part B tells us, well, let us find V out in phase 2 as a function of CA and Cref. Right? So, the idea here, the way you kind of think about what might we need to use in order to solve this question, we can notice that in phase 1, while we have this voltage source kind of to tell us about what's going on with this capacitor CA, we don't really have that same deal for phase 2, right? So generally when we're dealing with capacitors like this, we want to think charges, right? And charge sharing. So we can start by saying, what is the total charge in phase 1, right? So Q total in phase 1. Well, we know that's just going to be the amount of charge on each of the individual capacitors. So I can just say QA for the charge on capacitor A plus Q ref for the amount of charge on capacitor C ref. Okay? Now, remember from before, Q equals CV, right? The charge is equal to capacitance times voltage. So for QA, we have its capacitance is CA, and we have that the voltage across it, well, that's the same as VS, right? It's in parallel with VS. So this is going to be VS. Now, for Cref, however, we're told that it's initially uncharged, which means we know that the charge on it is going to be 0. Okay? So this is the amount of total charge that we have in phase 1. Now we can look at the total charge in phase 2. Once again, this is going to be QA and QRef. And I can just add in subscripts for 1 versus 2, right, because these values could be different. And now, in phase 2, what we see is that we have capacitor A and capacitor C ref in parallel, both with a voltage of V out across it, right? So the charge across capacitor A, well, that's going to be CA times the voltage across it, which is V out. And for C ref, similarly, it'll be C ref times V out. Okay? And we know that charge is conserved. So if charge is conserved, we know that Q total in first phase is equal to the total in the second phase. So we can equate these two. We have CA Vs is equal to CA plus C ref, just distributing the V out out. And this tells us that V out is equal to CA over CA plus C ref Vs. And as we can see, we're saying that we're writing V out as a function of CA and C ref, and we have achieved that. Yes? Standard procedure. Do you mind elaborating on that question? So charge sharing you generally think of when you maybe have like two different states, right? And you're trying to create a comparison between them. And here in this case, we needed to relate it somehow to what was happening with VS and these capacitors. And so kind of what we had here was like the charge to relate it. Because we know that the charge is conserved, so it'll be the same regardless of state, of which phase we were in. More or less, that's generally the situation you would use it in. I can't think of any other scenario off the top of my head. Any other questions? Okay, well, if that made sense, C is kind of a little extension of the same idea. Now we're saying, let this go for a couple more cycles. So we're at phase 1, phase 2, back to phase 1, back to phase 2. And now we're at the ith measurement cycle. Okay? So in phase 1, we are doing a similar thing. We're saying Q total 1. From before, we had the same idea that across capacitor CA, we're going to have CAVS. But what's going to be a little different here is the charge across QREF. Because what happens is in the previous cycle, right, you're going to have some V out left over from phase 2, this V out K here, that when the switches, one is closed and one is open, you're going to still have, right? And so you're going to still have this across C ref, you're going to have this voltage of V out from the previous measurement cycle, so it's K minus 1. Does that make sense to everyone? Yeah? Okay. And then Q total 2 really does not change much, except now instead of V out, we're saying this is for the kth measurement cycle, so we're going to denote it as V out K. So we have CA plus C ref V out K. Okay, so this is the kth measurement cycle. Once again, we know that Q total stays the same. And so, if we write this out, we have CAVS plus C ref V out K minus 1 is equal to Q total 2. So this is CA plus C ref V out K. And now we can solve for V out K, because that's what is asked for in the question. And we get CA VS. Sorry for the silence. Okay. And that would be it. Just to confirm, it says V out K in terms of V out K minus 1, CA and C ref. That is all we have here. So we're done. exactly. So when we come to the kth measurement cycle, okay, so this means we've just completed the k minus first measurement cycle, right? And so what that means is we're coming from this phase 2, where we have V out k minus 1, okay? And then we're going back to phase 1, right? These switches turn, but we still have this V out k minus 1 here, right? That's kind of maintained before. We still have that same charge that was on C ref, right? That charge on C ref, which we know from the previous cycle, would be C ref times V out k minus 1, and that's going to remain on this plate regardless of the fact that the switches have been closed. That this one's being closed and this one's being open. We're told that it alternates between phase 1 and phase 2 and starts at phase 1. Yeah. Yes. So the full cycle is going to be like phase 1 to phase 2, and then we measure the V out there, and then we go back to phase 1. Let me look for where it says this. It says it cycles through these 2 phases, right? It says up here. Sorry, I see that's off the screen. And so it says it pretty much cycles through these 2 phases and the switching, and we're saying that all capacitors reach steady state during each phase, right? And so when we're measuring it, it's achieved steady state. Yeah. Moral of the story, like questions like this, they have a lot of text before it. Just make sure to read through it. Make sure to check exactly what it's asking for and provide that. Okay.
All right, so next we're going to be looking at Norton and Thevenin equivalent problem. So take a few minutes to take a look at the circuit diagram. Just before we switch to the DocuCam, because it is a bit blurry. All right. I think we can switch back to, yeah. So just to get an idea, is this visible to everyone? Can people in the back see the circuit? Okay, I see one thumbs up, but anyone else? Can you guys see what's in the back? Okay. It's not visible at all? Okay. Let me try. Does this help? Okay, I see nods. Cool. All right, so let's get started. So for this one, you're asked in part A, redraw the circuit with all the sources nulled and calculate R Thevenin between terminals A and B. So as per earlier, this is one of the processes for finding either R Thevenin or R Norton. And what's important is to remember what exactly it means to null sources. So when we're nulling a voltage source, what do we do to that voltage source? What sort of component do we turn it into? Yeah, so I'm hearing shorts. How about for current sources? Open. Yeah, so we're going to want to break the circuit. So in this case, for the voltage source, we can redraw this as having a short in the place of where the voltage source once was. And then we can draw the rest of the circuit. In this case, for the current source, we'll put it open. And then we can draw in the terminals A and B, because these are where we'll be looking at the equivalent resistance for. So, oh, thank you. All right. So, if we're looking for the equivalent resistance here, there's a few things that we want to start looking for, which is, can we combine resistors in series, or can we combine them in parallel? Are there any that you guys know are in series or parallel in this configuration? So I heard someone say R2, and I didn't hear the second resistor. R3? Series or parallel? Okay. So those two are in series because if you look, they share a common node right here. And you'll see that there's nothing else connected to it because there's an open. And so we can combine these. So that's the first step that we can take for, redrawing the circuit and finding the equivalent resistance. So if we do that, we'll get this new resistance right here. What will that new resistance be in terms of the original resistances? I didn't quite hear that, but can you guys say one more time? Yes. So we'll have the sum of the two resistances. So once we have this, So I've not drawn in R4 here, but the thing is, if you look, R4 has this open terminal right here, right? The thing is, this is not really going to contribute to the resistances between A and B because it doesn't complete any like full paths, right? And so like, let's say if we did have something connected in this area, then we would expect it to see it contribute to the resistance, but because it's just open like that, it's not going to. There's a question? No. So like the next step we can take is when we can redraw this and remove that resistance. So in this case, what we really care about are these two resistances right here, where we have R2 plus R3 and then R1. So finally, we're left with two resistors. We can note that they have a relationship. They're in parallel. If you note right here, there's this node that they share, and then there's this other node that they share. So what we can do is replace that with the parallel equivalent. So if we redraw the circuit once more, we'll see that the parallel equivalent, R equivalent, will end up being just R1, and then we can use this operator with R2 plus R3. So if you want to write the entire expression out, it's going to be the product of those two resistors over the sum. So are there any questions at this point? All right. So the interpretation of this R equivalent that we're finding is that this is actually just R Thevenin. We could also equivalently say that this is going to be R Norton. Okay. So once we found this resistance, we can take a look at part B. In part B, they're asking, find the Thevenin voltage between... Oh, there's a question? Okay. So let's see. Could you switch back to the slides real quick? Okay. If we go back to the part where we're looking at Thevenin and Norton, right? So if you look in these diagrams, if I were to, like, say, I turn off the voltage source here, right, and I replace that with a short, then what's left in between terminals A and B? Just a resistor, right? So this is like this idea of if you turn off all the sources in your circuit, you're essentially left with just what's going to contribute to the resistance in that circuit. And so if you look at the equivalent resistance within the terminals A and B, you should expect to see just the Thevenin resistance. Or in this scenario, if you turn off the current source, it'll become an open. You're just left with that resistor. And so you'll only expect to see that Norton resistance. So this is the concept. This is one way to kind of like justify why you can say that equivalent resistance when you turn off all sources will just be either the Thevenin resistance or the Norton resistance. Are there any questions? Okay. Yeah. Thanks, Alice. All right. So for part B, we're asked to find the Thevenin voltage between terminals A and B, and they give us this hint, use superposition. So let's try approaching it from that method. So one thing about the circuit is that, let's see, I'll redraw the circuit down here so you guys can see. So if we have this circuit, then when we're finding the Thevenin voltage, we're going to be looking for this open circuit voltage right here. This open circuit voltage will just end up being the Thevenin voltage. So if we're using superposition, then we're going to want to turn off all sources except one. And so let's start with the voltage source. One thing I'm going to do in particular to help aid analysis is I'm going to choose a node as ground. If you choose a node as ground, then this can help us do node voltage analysis because it gives us a reference, someplace that we're saying is 0 volts. So I'll choose right there. You'll see why in a little bit why I'm choosing this node. But let's say I turn off the current source first and keep only the voltage source Vs. Then I can redraw the circuit as I leave the voltage source here in. I have R2, R3. I'm going to have an open if I turn off my current source. I'm left with this R4, R1, and let's see. I have my terminals A and B. And here, I'm going to want to label this V open circuit 1. So this is in particular because this is not the same circuit as before. But this V open circuit 1, if I add with the other V open circuit when I have the other source on, is going to give me back this original V open circuit. So from here, I'll reinstate my ground node. So if I'm analyzing this, I can see that there's this open path again, just like before. I'm not going to expect to see any current go down this path. So I don't really have to think about like how it will contribute to the circuit's behavior. So I'm going to redraw the circuit a bit to help me kind of like analyze it without having to think about R4. So first, I'm going to draw the voltage source Vs, and then, let's see, I'll draw R2. I'm going to rearrange the circuit a little bit. So the thing is, so long as I keep R2 and R3 connected, this is still going to be the same circuit. Next, I have R1 right here. And then you see right here where R3 and R1 connect, I have terminal A. So that's one way I'm keeping track of what's going on here. On the other side of R1, I have terminal B. And that's exactly where my ground node is. So if you look at the circuit, does this look familiar at all? So I'm hearing voltage divider. Yeah. So we can analyze this by looking at voltage division over the resistor R1. We'll end up getting that the V open circuit 1 will just be whichever resistor we're looking at, so R1, and then divided by the sum. So in this case, R1, R2, and R3. So we'll have R1 over the sum. And then we multiply by the source voltage. So this is just one quantity so far. We also have to look at, when we turn the current source on and when we turn the voltage source off. So let's do that on another sheet. All right. I'm just going to work on the back here. And let me redraw the circuit. Oh, thank you. Okay. So if I have the... Oh, it's off the screen. My bad. All right. Is this visible in the back? Okay, cool. So if we turn off the voltage source this time and leave only the current source on, then we're going to expect to see a short in the place of the voltage source. And then we'll have all these other resistors as before. And then here we'll have this current source. And you can fill everything in. So in this case, it doesn't look like there's a nice analysis method I can use like before. But I'm going to maintain the same location for ground. And so to approach this, I might think to myself, okay, I don't see anything nice happening with the current, so I'm just going to try using node voltage analysis because that's something I can always fall back on. So in this case, besides the ground node, how many other nodes are there? So I'm seeing 2 on a few fingers. Anyone else? Okay, so I'm seeing 2 and 3. So in particular, if we look at the circuit, we can point out that there's a node right here, there's a node right here, and then there's a third node right here. So we're actually going to have 3 nodes besides the ground node. So what we'll do with these nodes is we'll label them so that we can do our node voltage analysis. I'm just going to label them U1, U2, and U3. And I'm going to want to write my KCL equations at each of those nodes. Whenever you're doing node voltage analysis, you want to look at the nodes for which you don't know the voltage and write the KCL at those locations. So if I want to write my KCL equations, I'm going to have to label my currents. In this case, I don't have any labeled currents, so let's do that. If I look at that U1 node, I can label a current going through R2 into this node. I can label a current through R3 going out, and then we already kind of have a labeling from that IS. At this U2 node, I'm going to have to label a current for R4. I just happen to choose this direction. It's arbitrary. If you choose a different direction, you'll still get the same node voltages. And then for this R1, I'm going to choose this way. So now that I have all my current labelings, then one thing I can do is I can label the currents as well. So in particular, I'll label them to correspond with the resistor numberings. So I2, I3, and then I4. So if I write my KCL equation, let's see, okay, that's still visible. At U1, then I'm going to see currents coming in and going out, right? Which currents are going in? Okay, so I hear I2 is going in. So I'll put that first. And then what currents are going out? So I have I3 and IS, as some of you have said. So now this is one of my KCL equations. There's two other nodes for which I'll have to write them for. So at U2, here I'm just going to have this current source in series with the R4 resistor. So I can just say that the current through IS will be the same as this I4. If I happen to label this current direction opposite, then I might write something like IS plus I4 is equal to 0, in which case you know that they're opposite in sign. Lastly, at my node U3, I can write the KCL equation. Here I have a current through R4, through R3, and through R1. So I can write, for the currents coming in, what do I have? Okay. I'm hearing, I think you guys get the idea at this point, so I'll jump into writing it. But we can write the sum of I4 and I3 because they're coming in, and then we can write I1. If you still want, you can also write these equations as having like the terms going out where you have a negative sign and then set everything equal to 0. That's another valid way of doing it. So there's like at least 3 different ways of doing it, but do whichever way is most practice for you. So now that we have these 3 KCL equations, we want to substitute each of these current terms with expressions involving node voltages. So in particular, we're going to be using like these U1, U2, U3, and ground, which is 0 volts, to fill these in. So let's say we take that, here, I'll write to the side. If we look at I2, I2 goes from ground to the U1 node. And so if I were to do the passive sign convention labeling, I start at this plus 0 volts and go to the U1. So if I'm looking at the branch voltage there, that would be this ground node voltage, which is 0 volts, minus U1. And then if I want the current, then I have to take that branch voltage and divide it by the resistance. In this case, it would just be R2. Likewise, on the other side, for I3, which goes through resistor 3, I look at, okay, it starts at U1 and then goes to U3. So I can take that difference again, U1 minus U3. That gives me the branch voltage. If I divide by the resistance, then I'm going to get the current I3. So this expression right here, U1 minus U3 over R3, is going to be my I3. And then lastly, I have this known source value, IS. I can't really do anything with that, but usually these will be given to us, so I can leave that as is. For the next equation, again, I have IS, some known value, and then I can write expressions for the current through I4 by just taking the node voltages again. If I label according to passive sign convention, I have U2 as where the current starts and U3 as where the current goes to. So I can take that difference, U2 minus U3. This is exactly just a branch voltage over R4. Dividing by R4, I'll get the current. So any questions about this up to this point? All right. Are people following along? Are there like anything that's confusing about this? Okay. We'll jump into the third one. So for this U3 node, we can also write expressions again. So like let's say we take I4, we start at the U2 node, and then we go to U3. So that branch voltage will just be U2 minus U3. If we divide by the resistance, R4, then we get the current coming in. And then we can add the current going in as well through R3, which starts at U1 and then goes to U3. Divide by R3 to get the current. And then we know that this is going to be equal to I1. Looks like I've not left myself enough space here, but let's see if I can fit that in. It starts at U3 for the current through R1, and then it goes to my ground node. So I can say minus 0, and then I'm going to divide that by R1. So now that I have these 3 equations, I can put them into my matrix form or express them in some other fashion, like maybe just do algebra by hand to like figure out what my U1, U2, and U3 are. But once I do that, then I'll know that my V open circuit here, which will be V open circuit 2, will end up being just this U3 voltage minus 0. So if I find my U3 and subtract 0, this will just give me this V open circuit 2. So if I have this second open circuit voltage, then and let's say like you've solved these equations for what that node voltage is, then at the very end we can go back to what our original problem was, which was we wanted to find, let's see, the open circuit voltage here, right? So we found the first open circuit voltage when we turned only Vs on, and then when we found, was it U3 by solving these equations, then we get our second open circuit voltage. This open circuit voltage at the very end, where we have both sources acting together, will just be the sum of VOC1 and VOC2. So if we substitute in the expressions there, then we should be able to find what that would be. There's a question? Let's see. I1 and I2 equal. Yeah, it looks like it is. So you might be able to simplify your analysis this way. In particular, if I1 and I2 are equal, I wonder if it doesn't say anything about what U1 and U3 are, but I can't work that out in my head. But I would suggest, was it looking at the solutions, the key to figure out what's going on here? And then you can work out the rest of solving these equations by hand. Is another question? Oh, why did I choose this location as a ground node? Part of why I did this was to be consistent with what I did before, right here in the circuit. So I chose the ground node here because, I mean, eventually ends up as a voltage divider, right, which is convenient. If I chose some other location as a ground node, then it looks a little bit more hairy because I might have the polarity of that voltage like flipped upside down. So it's not like I'll have to add some negative signs and stuff. So, but because I chose a ground node at this location here, then I'm also going to want to do that here so that if I find like a node voltage, then this is going to be consistent with like the previous situation. So if, let's say I didn't choose the ground node in the same location, then what I would have to explicitly calculate is like the difference in voltage between this node and this node, and that would be my VOC2. But yeah, like doing it this way gives me the convenience of if I just take this node voltage right here, that will just also be my VOC2. So, and it's also consistent with what we were working on before. So it's not a choice you have to make, but it can help simplify things if you like have consistency. Are there any other questions? Yes. Mm-hmm. Yeah. Yeah. Let's see. So you're saying replace what term with IS? Yeah. Mm-hmm. Okay, so you're saying replace this with IS. Okay, yeah. Yeah, that's definitely a valid approach. So here I'm just going the long way around because I don't immediately see like structure that might help me. But if you happen to notice, then by all means leverage that. Yeah. So it's completely valid if you notice like certain relationships hold. It can speed up your analysis. Was it? And the thing is, it takes practice. So if you don't have that right away, then you can always go back to node voltage analysis. Yeah. All right. If there are no further questions, I think we can move on to the next problem. All right, cool. Oh. Yeah, I think let's do this one. So there is a Thevenin circuit problem that you're asked about that we're skipping, but this one is pretty much like, this doesn't have any sources, so you're not also going to see any sources in your Thevenin equivalent. You're just going to end up seeing that your equivalent ends up being a resistor. So I'd recommend trying this one out as practice if you can find it on the slides later. But essentially the idea is if you don't have any sources in your circuit, you're not going to have any sources in your equivalent. So, all right. Any questions on that? In this case, yeah, VTH will be 0. You're just going to get a short. All right, cool.
Okay.
Okay, so I guess I'll give everyone a question or a few minutes to read over this question as well, and then we'll try to discuss together afterwards.
Okay, so let's take a look at this question together. Can people hear me at the back? Or yeah, okay, great. So here we have like two telephone cables between city A to city B. I guess telephones are a little bit old and people don't really use landlines anymore, but let's say this is important to think about. So in this case, we find out that at some unknown location C, we have sort of like a broken wire. So now we've like shorted out some wire between these two at this location. We also know that city A and city B are 100 kilometers apart, and then we know something about the resistance of our cable. Okay, so now we want to try to help the technician figure out where the break is so that they can go over and fix it. So the first part of this question says that we'd like to build a model of the telephone wire by modeling what the resistance is of our wire. And so we can regard the telephone cable from location A2 to location C as a single resistor, RA2C. Okay. And then we know the distance between A2 and C is going to be X kilometers. Let's try to figure out what the resistance of RA2C is. Okay. So first of all, one thing that we can notice about this is that we're given something for the resistance, right? We know that it's going to be 6 ohms per kilometer, and we know the units for resistance, right? It should be in units of ohms. So in order to get ohms at the end, we need to multiply by some sort of distance to convert our ohms per kilometer into the right units. So what units, or what things should we multiply by? X, right? Yep. So X is in units of kilometers. So we know that RA to C should just be 6 ohms per kilometer multiplied by X kilometers. So that should give us 6X. 6X kilometers. Okay. Okay, sounds good. And so now let's try to take a look at the second part of the question. So now in order to figure out where or exactly what the location of C is, we're going to attach this testing circuit between A1 to A2, and we know something about the resistors. So now I'll let everyone take a second to try to figure out how to go ahead and calculate that. Okay, so basically we have this circuit that we've kind of attached to our original wire, right? And we know something about like this resistor here. This guy is RA to C, and we know that's going to be 6X ohms. And this wire should be the same, right? This is also RA to C. 6X ohms. Okay, so for convenience sake, I'd like to redraw this circuit to make it look a little bit easier to digest. So what I'm going to do is I'm going to go ahead and move this voltage source over here. And you'll notice that at this node, we have two resistors connected to it, so R1 and R2. U1 is located next to R2, and there's a current going from U1 to U2 over here. So I test. And then after that, underneath U1, I have 2 resistors, so RA to C and then also RA to C. And then underneath U2, I have my R test. Okay, and then both of these guys are both connected to ground. Okay. And so we also have some really useful information that was given to us in this circuit. So one of them is that we know that I test equals 0. And the other one is that we know that R test is 480 ohms. Okay, so if I have a I test equals 0, I guess some people have some questions. Okay, let's start with the questions. Okay. So if I were to go ahead and draw this out, so let's say I have U1 here, right? So that's corresponding to this node here. So you can think of it as like there's like some pathway here across RA to C up to this node, right? So let me call this U3. Okay. So in this case, this U3 is only connected to one other resistor, which is the other RA to C, right? And so that matches up with this circuit. I have some node here called U3, and nothing else is connected to it, right? That's where my short circuit location is. If I take a look at the second RA to C, going from U3 and going through this resistor, at the other end down here, there's like a ground symbol connected here, right? And this R test is also connected to this ground symbol. And so here I've just drawn 2 ground symbols. And even though I haven't drawn a wire connecting the 2 ground symbols together, whenever we have like multiple ground symbols, it's implied that all of them are connected to the same node. Yeah. Okay. Any other questions? Yeah. Okay, so that's a really good point. So what I wanted to get at is, so first of all, you are right that all of this U1 and U2 is actually the same node, right? But having a same node, I guess, what sort of information does that tell us? Does that tell us about the current, or does it tell us about the voltage? Yeah, it tells us the voltage, right? And so because we have the same node, basically that means that U1 equals U2, so the voltages are the same, right? But having a same node doesn't mean that there's necessarily no current going through this wire. So for example, if you had, if you were to do KCL at this location, it could be that my input current, so maybe I'll just go ahead and try to draw some on here to illustrate. So let me label this I2, IA to C, and I test. This guy can be maybe I1, and then this one can be I test. IR. So if we kind of were to do like KCL at this node, right? It doesn't, because we normally consider this whole thing as a node, we don't think about whether or not there's any current going through here, because we just consider like these 4 red currents, right? All the currents coming in from a branch or going to a branch. But in actuality, right, you can have current going through I-test, right? This is not necessarily always 0. It's only 0 in like a special situation. What's that? So in this case, the sum of all the red currents, so I1 plus I2 should minus IR minus IA to C will equal 0. But when we consider I guess KCL,
across the entire node, then that's not saying anything about this I test. Yeah, normally we kind of ignore that. What you could consider is like the situation where you kind of ignored half the node. So let's say that I just consider the right side, right? So here I'd have like 3 currents. So I2 is coming in, I test is going out, and IA to C is coming out, right? So in that case, the sum of all 3 currents is going to be 0 as well by KCL. In that case, I test is only 0 if I2 equals IA to C. But that's not always true, right? It also depends on other things. Is there a question back there? Yeah. Yeah, okay. So let me maybe illustrate what I'm trying to say here, right? So let's say that this is kind of a side example, but I just want to explain like a subtle point here. So let's say I have some voltage here, right? I have some node called U1. Let me draw another node called U2 and put a resistor here. Okay, so everyone agrees that the potential at U1 and at U2 is the same, right? But is there any current going from U1 to U2? There is current, right? Because I have some resistor here, I know that there will be current flowing from my voltage source through the resistor. So it's the same thing going through I test. There can be current going through here, even though the potential at each side of the node is the same. Okay, so the fact here that I test is equal to 0 actually tells us something very special. Does anyone have an idea of what that might be? So I test, so if we do KCL at one of the node U1 or U2, we can sum up the currents coming in or leaving the resistors. But if we know that I test is 0, that's the same thing as if we were to sort of zero out a current source, right? So when we zero out a current source, how do we treat that? Yeah, we treat it like an open circuit, right? So that's actually something that we can do here as well. Because I test equals 0, open circuit. Okay. So in this case, we can treat it like an open circuit, but U1 and U2 still have the same voltage. Okay? All right. So next, let's think about what happens if we do that. So let me go ahead and try to redraw my new circuit, treating this as an open voltage, or open circuit, sorry. And so just to simplify things, you'll notice that this resistor and this resistor are in series. So I've just combined them here. So I've added the 2 resistors together, right? And so is there any way we can calculate what the voltage at either U2 or U1 is? So if we take a look at what the voltage is here, right? We know that the voltage here is going to be Vs, right? Because you have 0 volts here, and then this node has Vs voltage higher than that, right? And so if we know the voltage here is set, and I have 2 resistors in series, is there some way we can calculate what the voltage is here? I think I hear some people saying it, but they sound a bit unsure. So maybe, yeah. So both of these can be treated with voltage dividers, right? So if I were to do a voltage divider to calculate U2, I can calculate the voltage as U2 is going to be this original large voltage Vs multiplied by the lower resistor divided by the sum of the 2. So our test
over R1 plus R test. Right? And I can go ahead and do the same thing with U1. So U1 also equals Vs times 2RA2C over 2RA2C plus R2. Okay. And we also know that U1 equals U2. Oh, sorry. Okay, thanks. So we also know U1 equals U2, right? So these voltages are actually equal to each other, right? Okay, so let's go ahead and substitute some numbers in. So let me go ahead and set U1 equal to U2. So we'll get Vs times R test, which they told us is 480 ohms, over 1,000 ohms plus 480 ohms. And this equals Vs times 2 RA to C, which from before we said was 6x ohms, over 2 times 6x ohms plus 1,000 ohms. Okay. So something helpful to know is my Vs's helpfully cancel out. And so we can go ahead and try to solve this for x, right? Because we have one unknown and one equation. But there's actually kind of an easier way to do this. Does anyone notice something kind of interesting about this equation? Yeah? Yeah, exactly, right? So because this bottom resistor here is equal to each other, we can observe that if we set this resistance equal to this resistance, then these two equations, like this equation will be satisfied, right? So we just have to set 480 ohms equal to 12x ohms, right? And then now we can go ahead and solve for x. So x is going to be 480 ohms divided by 12. And so that will give us 40 kilometers. Okay. Okay. Let me double check. Okay. Yeah, question. Could you solve for x by getting the equivalent resistance between what and what? Oh, okay. So one thing you could do, so if you were to go ahead and calculate the equivalent resistance, you can do that, but the key thing to note here is that you don't want to get rid of U1 or U2. So ideally, what you really care about, right, is the voltage at either U2 or U1. So like, for example, like here you'll notice that like these two resistors are in series, right? So if I took the equivalent resistance, basically what you get is like R test plus R1, right? So this is going to give us something like this. R1 plus 2RA to C. And so now we don't know what U2 and U1 are anymore. So one thing you could do is like you can use that to calculate what the current